Okay, running through our setup here. At the moment we're simply driving our bifilar pancake coil with my function generator here, 866 kilohertz. This situation works over a wide range of frequency in the higher end, so the difference becomes less and less the lower the frequency, but it does not have to be at its resonant frequency. So we will change that value a little in a bit later on in this video, but that's what we're running at the moment. Our scope at the moment is isolated from my mains ground, and I've done that simply by running it off of my caravan, which is off grid, and this scope is running off the inverter, which allows us to be ground isolated to my function generator. So on one end of our bifilar pancake coil we have a 100 ohm resistor, as you will see, brown, black, brown, and we have the scope across that resistor to get our current flow going into the coil. So it's 1.36 volts RMS over that 100 ohm resistor. You'll also see another 100 ohm resistor here. I'll get that clear, brown, black, brown. Now that is between the centre tap of the coil, so we've in this case it goes into the middle and winds out, and then of course we come back from the outside to the middle and wind out again and come out of the positive. So that is the centre tap of our coil. Here you'll see a little LED with two clip leads. That is just to verify what the scope is showing us, and the scope is not showing us something silly. So that's what we have, a 100 ohm resistor on the input, being AC, it doesn't matter whether it's negative or positive because it's both, and another 100 ohm resistor at the centre tap. Now the current flowing through a coil should be the same all the way through that coil, so we're about to see something a little different here. So once again, 1.36 volts RMS across our 100 ohm resistor there. We're simply going to take our scope now and put it across the resistor that's in the middle of the windings of the coil, like so. And we now have 2.48 volts RMS across that 100 ohm resistor. So the current flowing backwards and forwards in the middle of the coil is more than the current flowing into the coil, whereas normally in any other coil that I know of, the current in any one point of the coil should be the same. So what we're going to do now to make sure that our scope isn't picking up some sort of RF and making its own voltage across the middle of the coil, we can of course stand our wires vertical like that, so the loop is vertical to the windings on the coil, and you will see the result is the same. But to confirm what our scope is showing us, I'm going to place our LED wires across our input resistor. Remember we're AC, so it should fire up one way or the other, and you will see that we get nothing. So the next position of course to try is across our centre resistor here, like so, and you will see the LED is happily glowing. So that's confirming what the scope is showing us, there is a higher voltage across that 100 ohm resistor, which is in the middle of the windings, than there is on the input. Now, like I said, this is not at the coil's resonant frequency, and we will simply bump it up to 966 kilohertz, and we will carry out our test once again. So now we have 1.24 volts RMS across our input resistor, which once again is 100 ohms, and I'm using a high value resistor so I can reduce the noise level across that resistor. And once again we'll check our center tap resistor, and we have 2.56 volts RMS across our 100 ohm resistor. So the current flowing through this coil is definitely not the same all the way around. Once again, our LED light's nice and bright, and if we put on this resistor, the LED doesn't light at all, which is once again confirming what the scope is showing us. Now, as we go down in frequency, this difference decreases in value, so we will put our scope back on our input resistor like so, and we'll go down to 566 kilohertz. Now have 1.88 volts RMS across our 100 ohm input resistor, and across the center tap resistor once again we have 2.4 volts RMS. So it's not a resonant frequency phenomenon where all the current is flowing through the coil or being maintained within the coil. Chuck our LED across there once again. We can see it shines nice and bright. We'll now put it across the other resistor, our input resistor, and now it is ever so dull because our current is starting to become even the lower we get in frequency. But as the frequency climbs, that difference gets greater, and so we now have a coil and a situation where the current flowing through the middle of the coil is not the same as the current flowing into or out of the coil. So something very interesting that I've only found with this. I have tried other coils, actually have put resistors in the middle of the windings of other coils, and I have not seen this before. So I suspect it's got something to do with the self-capacitance of the coil and the voltage potential between each windings, which is giving us an increased current flow in the middle of the windings of the coil, which results in a higher current flow than what's actually flowing into the coil as well. But something worth looking into. What I might actually do while we're at it, so I'll wind that back up to 966 kilohertz, and there's nothing special about that frequency, as I said. It's just turning the knob, making it work. We'll turn that back on. 1.24 volts RMS is the current. I haven't tried this, but we'll do it on the fly. Hook our LED up and see what happens to our input. Okay, so once again 1.24 volts RMS. LED is now on, as you can see, fairly bright, and that has not changed our current input. What's 1.24 volts over 100 ohms is 1.24 milliamps, or 12.4. Don't know. Haven't got my calculator. So there you go. Not seeing any difference whatsoever by placing a load across the centre tap of our coil. It doesn't even change the waveform, so it's disconnected. I'll hook it back up again. And it's now connected. Nothing. So now we'll just place a dead short across that resistor, see what happens. Like so, and the current actually went down and not up. So that's the short on, and that is the short off. Okay, so we placed a dead short across our 100 ohm resistor and the input current went down, apparently. Anyway, that's what I've found that's different so far. The current flowing through the centre of the coil is higher than the current flowing into the coil. Right, thanks for watching, and give it a shot yourself, see how you go.